Hello, this is part 2 on our section about high order polynomials, and we're going to work through an example, and this involves the minimum baseball salary for Major League Baseball players from 1967 to 2017. And so we have 6 data points, so it's not a huge amount of data, but we're just going to use it to illustrate some points here. And what we'd like to do is find the polynomial that will fit this best and then compare that to a lower order polynomial and decide what is our final choice for the model we would use. And to help us analyze the model a little bit, I have included some interpolation type of data that falls between our data that's year by year. So we'll use that here in a minute. But for now, let's focus on this data. And the first thing we would say is that notice we have some really large numbers here. And so let us make our X in terms of years since 1967. So 0, 10, 20, 30, 40, 50. And likewise, our Y values, we don't need all these extra zeros. So we'll divide everything by 1,000 to get 619, 62.5, 150, 380, 535. All right, so that will be our data set, and let's go to a computer algebra system and analyze it. So this is Maple, and if you need to know more about Maple, I invite you to check out Chapter 3, where we'll go through computer algebra system basics. So I'm not going to do a lot of typing. I'm going to just go through it line by line. But again, if you're uncomfortable with it, you can watch those other videos to get more familiarity. So we load a package here that allows us to do point plot. And then as you can see, these are exactly the data points that we just referred to previously. And so here's a plot of that data. And we see that there is some sort of a trend. It's definitely increasing, appears to be concave up for the most part. And so let's go ahead and fit a polynomial that will hit every point precisely because the X values are distinct. And since we have 1, 2, 3, 4, 5, 6 data points, we need a 5th degree polynomial. And I'm going to have my coefficients go from A0 to A5. So those are the unknowns. And so now I need to solve a system of 6 equations and 6 unknowns. And Maple can do that in one command line here. So these are the equations here at the front end. Notice I want the function, my polynomial, to pass through 6 when x is 0. I want when x is 10 for y to be 19 and so forth. And then I tell Maple what are the variables I'm solving for, A0 through A5. And if you're curious, we can see how long it takes to do that. And notice it's almost instantaneous. I can plug in, and so here is the best fit polynomial that should pass through the points precisely. If we want to confirm that, we can plot the polynomial and then place it on top of the previous point plot and get a single plot. And so here it is. And sure enough, the polynomial does pass through all points. Now, immediately we see something a little problematic. It's showing some negative salaries, so that could be a concern. But other than that, for the points themselves, no problems. So here you can see we have a way of interpolating and extrapolating the function by just plugging a number in. So if I want to know what happens in year 7, I can evaluate it, and Maple tells me that the salary, remember this should be multiplied by 1,000. Minimum salary is $33.64, which is actually probably low because a few years before it was at $6,000. And let's say we wanted to try extrapolation. We can plug in, say, 70. Also a problematic number. Now we're getting a negative salary. Maybe not a surprise because we can see the polynomial starting to curve down. So it must actually continue to go downward, which 70 years, that would be in the future. So no one knows the future, of course, but we can be confident that it's not going to be negative. All right, so since we have some flaws and some concerns about this polynomial, we can try some smoothing. And some smoothing would be to pick a quadratic. So this is the quadratic that Excel gives if we just do the least squares regression. And we'll see that on Excel here in a moment. But to see what that looks like, we can graph all three. That's what the display command does, is it lets me show all three plots at the same time. And so here's that plot. The quadratic also does a nice job of capturing the trend of the data. There's certainly some error. We're not passing through all the points, but it also doesn't have negatives. And of course, the quadratic, as we know, is going to continue to increase, so we don't have to worry about it all of a sudden becoming negative. In fact, if we wanted to, we could plot this out to 70. And we can see at 70, it's predicting a number up here somewhere. So certainly a lot more believable than a negative salary. What about those salaries for the halfway points between each decade? So that's this data right here. So that gives us a little more information to work with. And we're going to put those points in green for comparison's sake. And so when we overlay that new data on the old functions, we can get an idea of how well each polynomial fits. And we can see that certainly it's not going to be perfect for either one. Here's a point where the quadratic is actually better than the quintic, the fifth degree polynomial. And looks like the quadratic is probably a little better on a couple of other points as well. And then maybe the quintic is better on these last two. So that gives us a little bit of a feel for how Maple can help us analyze this sort of problem. Let's use another approach, and that's the sum of the squared error like we've done before. And for that, we can go to Excel. So here on Excel, I've already typed in all the data. So here it is, both the original numbers and the extra numbers. And I went ahead and typed in the models for each one. So notice here's the quadratic, so there's where that function came from. And if we plug that in using our year since 1967, we can drag that down. And as always, we want to make sure, is it predicting what we expected here? 68.2 versus 62.5. That looks okay. How about here at 40? Looks like it's predicting 300. So that doesn't seem too bad. A little bit above. So it looks like this is in fact matching our graph. So we can calculate the sum of the squared error, which is our usual formula. And so if I drag that down, we don't need these empty spots. And so we get an SSE overall of 7391. Now this is a little bit strange because I'm including the interpolated points, but it's just a way of measuring the quality of the fit. And now here's the quintic model. Notice this is the same equation as we had from Maple. And this is a few enough data points we actually could let Excel calculate it for us. Notice we get an R squared of 1, not a surprise, perfect fit. And we get the same values, although it's a little hard to tell because notice there I have the scientific notation. So Maple gives us the more precise values as we saw right here. So if we go back to Excel, I can drag down our quintic model. And there's our negative value that we were concerned about. We'll drag this squared error down as well. Once again, if we look at squared error, we can see how the quadratic is better for 3 of the data points and how the quintic is better for the other 2. Now, of course, the quintic is basically going to be perfect for these first 5 points. So when we compare the two, the quintic is certainly going to be better overall. Now, depending on what we're trying to do with this model, either one might be the better choice. If we want extrapolation, I would go with the quadratic. Of course, that's dangerous no matter what model we pick. If we're wanting to just fit the data and the shape of the data, the quintic is of course better, but be aware there are a few places where it's not going to be as good as the quadratic. So depends on your goal, but that is our conclusions as of now. So that's it for this example. We'll go a little deeper in the next one, so check out the next video for that.